All right, we'll be starting here shortly. Give me a second, guys and gals. All right, it's another Q&A Friday. Making things happen on a Friday. Ryan Jackson in the house. Well, Ryan, we're going to have to do, we should be doing another Q&A Friday. I'm getting notifications that they want you on more often. So we're going to make that happen, brother. I'm waiting for a package. So I set up a we'll be right back screen. What do you think of that? All right. So Q&A Friday. I can't believe it is Friday the 15th. A couple things. First, next week I'm going to be at a ASHE, ASHE. I think it's American Society for Healthcare Engineers. All right, Ryan. Well, we got to come up with another topic for maybe next Friday. Maybe next Friday we'll do another topic. We just got to think of something cool. I'm going to finish out. I might try to finish up the 112.5 transformer today. Because I can run some. I could pull up the SCAM stuff. But ASHE annual conference is next week. So ASHE annual conference. I'm going to be speaking. I'm doing we're doing a session out there. Hey, not me, sheltering, baby. Sheltering. So, hey, Varun, good to see you, brother. So I am, I'm going to be at this ASHE conference. How do I get, is it control? Yeah, there it is. Look at that. I'm learning. John Doss. Hey, Arkansas, you are the man. Not me is here. Nihad El Sharif. Happy Friday. Varun, Shelton, John Doss, and Ryan Jackson. So next week, I got something cool. We're going to be Willie Snyder. Next week, I think on Tuesday. I got to look at what time. What time on Tuesday? Advocacy, get involved about, so hold on. There's the ASHE conference, Boston Convention Center, early bird. I'm looking for the schedule. I've already registered. There's Eaton, blah, blah, yahoo. All right, so exhibitors and sponsors schedule, speakers. See if they got me in here. They should. And hopefully I will be able to tell you when, because, so here's the thing. So I'm speaking next week, but I'm not going to be, here I am. View profile. No, they don't have me. They don't have the program. So let's take a look at the schedule. So I'm going to take my stuff and we're going to take the booth live next week. I believe Monday. We're going to go live on Monday. I'm speaking on Tuesday. We're going to go live on Monday. So July 17th. What's today? 15, 16. That's Sunday. Monday is the 18th. So 18th. This is the schedule. They got the welcome and awards. They got compliance lounge. Apparently, I've never been on TV, and apparently, where's it at? Next General, ASHE's new terror. Where's it at? What are the costs? Compliance, exhibit hall, 4:30 to 6:30. We'll probably go live somewhere in that ballpark, 4:30 to 6:30. But there's an earlier session, exhibit hall. I thought in the morning, in the afternoon. I guess not. All right, so we'll see. Here's what you got to do. You're going to have to, if you're coming in on like Mr. Kazi coming in on LinkedIn, Well, you've got to be following me. So I'll probably just do YouTube. I don't know. I might go live on my LinkedIn account. I'm not sure yet, but it'll depend upon how it goes. But so Monday night looks like I will have on the 16th. Is that what's Monday? What's Monday? Monday is what? Monday is 16. Monday's the 18th. Okay, Monday's the 18th. So it looks like they have the exhibit hall happy hour 4:30 to 6:30. We'll be going live probably from the booth then. So hey, Dirty Mike, you got to get in there. You got to Monday. We're going to be live from our healthcare booth at the American Society of Healthcare Engineers. Now on Tuesday. 10:45 to 1:45. So we'll go live on Tuesday, 10:45 to 1:45. I got to find out when my presentation is. My presentation is. It's not a presentation. We have a group of us talking. I think this is me. Yes, there we are. Electrical safety roadmap. I'm going to be with Mary Alcaraz, from Senior Project Manager at Children's Hospital of Philadelphia. Aaron Harrington, Engineering Group Leader at Bellinger. Justin Caron, he is Segment Director for Healthcare and Life Sciences with Eaton. And then me. And we're going to be talking about the living, breathing building. And this was Justin's concept. And we wrote like a series of articles for the healthcare engineers talking about the design phase, the installation phase, and then the continued existence, of the structure. And we call and Justin's comment was it's a living, breathing building, and I agree with him 100% because you think about a structure. Especially healthcare, they change those structures over time. A lot of stuff goes into continuously improving and changing that building, whether it is growing the building, changing the infrastructure, whatever it is. So in this section, we're going to offer a perspective from a design from these. We've got, I think, 4 key individuals that, including me. 300.15 for 2023. We'll take a look at it, Willie. But I want to let everybody know, if you're not subscribed to my YouTube channel, get over there, subscribe to it, hit the bell. I'm going to go live at least on the YouTube. I'm not sure about LinkedIn, Facebook, and all this other good stuff. So I'll at least be live from the booth on YouTube, so you can get over there. And I'm not sure when. What I'll do is I'll look at the schedule and I'll set up a couple live streams that you can bookmark. And if I go live at that time, anytime, I will just, I will hit it, go live. But I got to make sure I got internet at that booth and all the other jazz. So you're going to want to subscribe and hit the bell on my YouTube channel. All right, so let's take a look. 300.15. /70 next. And we got some news, 210.8. Before I do that, the TIAs, we had some certified amending motions on 210.8F for outside outside equipment. I don't want to say HVAC, but the HVAC industry is having some challenges right now because of they use that equipment grounding conductor, unfortunately, and it causes a conflict with GFCI. So Sarah Caldwell had sent out the final ballot information from the correlating committee. So here's where we ended up on 210.8F. Remember, the certified amending motions all failed at the floor at the annual meeting. The TIAs, there were 2 TIAs put in for the 2023 code. One of them said, provided an exception for any listed HVAC equipment. And the other was, I don't know if you know Dean Hunter from, I think he's Minnesota. I think. Anyway, Dean Hunter had put we had accepted a TIA last cycle, which gave an exception for, I'm just going to look at what the technical committee ballot, we put an exception for, it wasn't 1656 TIA, it was 1657. So last cycle, we had an exception just for like HVAC equipment that has variable frequency drive technologies in it and split unit device HVAC equipment. And here's what it was. Here we go. I'm going to try this. I'm going to try this. I'm going to try it. I'm going to try it. Here we go. There it is. So this language added an exception, and this passed for a TIA. Hey, Collins, great day again. Another great day. We're on the right side of the grass. Exception number 2, GFCI protection for mini split type HVAC air conditioning equipment and other, and it has a an expiration date, September 1st, 2026. So we got a stay of execution, so to speak, for this equipment. Now that was the technical committee. The technical committee passed that one, didn't pass the other, which was if it was a listed HVAC equipment, that didn't pass at the technical committee. The correlating committee passed them both. They passed. So correlating committee accepted the TIA that provided the exception for all listed HVAC equipment, and they accepted the TIA that only permitted an exception that was shown here for split units and units that have compressors that have power conversion equipment. So I'm thinking, and I have got to get confirmation on this, when the correlating committee passes them both, which actually I think creates a correlation issue because they both modify the same exception. So I think that there's a correlation issue if they passed them both, physically tried to put them both in. So I think what NFPA will do, and I don't know this for sure, I'm still trying to get confirmation, but time will tell. I believe that NFPA is probably going to accept what the technical committee and the correlating committee agree on as the final language, which is the exception I just showed you. So anyway, that I believe is behind us. The only thing that has to happen now is Standards Council. There's another one too, panel. Oh, Ryan Jackson, the barriers, the energized 215.15, the word energized is going in, so that solves that problem. That's been accepted, and I believe that is pretty much good to go. All right, so I need to look up 300.15. Now, I will say, Willie, I'm going to look at 300.15. I am not on that code making panel. And you all know that no matter what I say here, it originates here, it comes out here, but it's all from here, right? It's not on behalf of the panel. It's not on behalf of NFPA, Eaton, correlating committee, and all that good stuff. Hey, Nihad. I was confused too at that correlating committee direction. I would have thunk that the correlating committee would have picked one or the other, but I don't know what the heck was going on, because technically, if the technical committee didn't pass the one TIA, but they passed the other, I would have thought that only the one TIA would have gone to the correlating committee and not the other, because the technical committee didn't accept the exception for just all listed equipment, HVAC equipment. So I don't get that. I don't know. I must be naive. All right, so I'm going to take a look at 300. 300.15. 300.15. And if you guys did not get a chance to take a look at the IEI News Live series on Transformers, please get over there. We had a good time. We focused on the 75 kVA. And before I get off, I think I'm going to try to do the 112.5 kVA on the fly. All right, so 300.15. I'm in 300.15. Boxes, conduits, and fittings. Apparently, I'm not, hold on, NFPA 70. I got them waiting for a package too. I have to sign for. So if I throw up the "I'll be right back" message, that's all I got to do because I got to sign. If I don't sign, they take it back. All right, so let's take a look at the first draft. Willie, I think the change that you're looking for in 300.15 actually occurred in the first draft. 300.15. All right, here we go. 300.15. Oh, okay. In 300.15 parent text, they said where the wiring method is conduit, tubing, type AC cable, type MC cable, type MI cable, non-metallic sheath cable, or other cables, a box or conduit body shall be installed at each outlet point, switch point, conductor splice point, conductor junction point. So they added conductor splice point, conductor termination point, wiring method transition point, or conductor pull point. That's what they did in the parent text. Are you asking about that? Listing of transition fittings. Well, if it's a listing requirement for a transition fitting, it's just, it needs to be listed. I don't see where it says listing. I don't see where they added the word listing. Transition points. Fittings. A fitting identified for shall be permitted. That's already existing language. I was wondering if I was reading it right. You know what, Willie? Why don't we do this? Mr. Jackerson, or Willie Snyder, and Jackson, Ryan, I am going to do this. I'm going to create you. Oh, Willie, are you someplace where you can talk and get online? The problem is in F. We don't list fittings. Come on, guys. I'm going to let you in. Hold on. I'm going to let you in. Ryan and Willie, I believe the link is right there. Click on Google Meet and let's get you online. Huh? Come on. Willie, I'm going to answer that question, but we're going to do it together. All right, brother? From another mother. Come on into the... come on in and I'll throw you up on the screen. All right. So I'll wait for you, but I don't see that. I don't see that. What you're talking about listing requirements. He says the problem is in F, fitting, and they didn't change it in the first draft. And in the second draft, they didn't change it in the second draft. So what's the issue? There's no change in F for the 2023 code. And it says a fitting identified for use shall be permitted in lieu of a box or conduit body where conductors, a fitting identified for the use shall be permitted in lieu of a box or conduit body where conductors are not spliced or terminated within the fitting. The fitting shall be accessible after installation, unless listed for concealed installation. A fitting identified for the use shall be permitted in lieu of a box. Something's reminding me that, hey, there we go. Shall I admit? I am admitting. Mr. Jackson, I presume. Shall I admit? I know you can hear me, brother, but you're listening through your speakers. How are you, sir? I know you can hear me, brother, but you're listening through your speakers. Yes. All right, so I've got you under my skin, Mr. Jackson.
I need to grab my headphones, buddy. Hang on.
All right, get your headphones. He's going to get his headphones, and I am going to.
Let's see.
I'm going to spotlight him. How do I spotlight? He can't find his headphones. How do I spotlight? Oh, there we go. All right, so here's what we're going to do. Guest one is going to be a window capture. Chrome. Here we go. All right, so we're going to get we're going to have a good time. This is how we roll. I guess Willie Jackerson can't make it in, but that's okay. Because we are going to talk a little bit about .310, and we are going to kick some butt. I'm just setting him up. All right. This is how we roll. This is how we do it. Studio. All right. So if I do guest and I do me with guest one, and we got Nihad El Sharif. We got Nihad El Sharif, guest one name. This is Ryan Jackson.
There he is.
How's it going, Ryan? Can you hear me? You can.
I can hear you now, buddy.
All right, cool. All right, so I'm looking at F. It says a fitting identified for the use shall be permitted to in lieu of a box and or conduit body where the conductors are not spliced or terminated. So you said the problem's in F. Is it that it's listed, or that I guess you're saying? I guess you can't. No, you can't hear me. He says
I can hear you. I can hear you, but I'm hearing you twice.
Oh, really?
Yeah.
Oh, that's weird. Take it easy on CMP3, Tim.
Oh, you know what I got to do? I got to mute you on YouTube.
Yeah, you mute me on YouTube.
Okay, sorry.
There we go. That's it. Take it. So Tim wants us to take it easy on Code Panel 3, buddy.
This is Tim's fault, so you know.
Oh,
no. Tim knows that there's a problem in 300.15. He and I have talked about it, and 300.15 is a big section, and it covers a lot of ground. And as you know, Tom, I mean, you know, some people say that I hate the code and I'm always saying how bad the code is, and other people say that I'm an apologist for the code and I can never point out problems. And you know, it's somewhere in the middle. I mean, 300.15, it's tough to write good code, and 300.15 is a big section. So 300.15, the first thing it says is that fittings have to be listed for the wiring methods in which they're being used, which is a good rule. And then it says you need a box if you're going to make a splice or you're going to make a termination or something like that. And that's a good rule. We need boxes at our terminations.
Yeah.
But it also says that we need boxes at a pull point, for example, which is also a good rule. And then it says, unless allowed by, I think it's A through L, and it gives a bunch of exceptions. Now, one of those exceptions is a fitting. So I don't need to have a box at a pull point if I'm using a fitting. So take like a Flex 90, for example. That's a pull point. And that fitting, I don't need a box because I'm using the fitting. But it's also imperative that that fitting remains accessible. I can't bury, literally or figuratively, a Flex 90 because I need to be able to take that cover off to be able to remove or replace the conductors or insert the conductors.
Right.
So that's a good requirement. But they made a change in the 2020 code that was kind of based off of a misconception of what that section really said. And it said, okay, well, you need a fitting, or you can use a fitting in lieu of a box, but it has to be accessible after installation, unless listed for concealment. Okay, well, we don't list fittings for concealment. You can conceal the wiring method, but fittings aren't listed that way. That's not how we list fittings. So are there any fittings that are listed for concealment? Well, not really, because that's not a thing. You can conceal them. I'm not saying that you can't, but what we screwed up even much more severely in the 2023 code is now we're saying that we need a fitting or a box at a wiring method transition to go from Flex to EMT, for example. And of course, you can use a fitting that does that. And there's no reason that fitting would ever need to be accessible. There's no reason whatsoever. So they're saying, well, it can be concealed if it's listed for concealment. But again, there's no such thing. So another example would be when you're underground going from PVC to a rigid 90 or an IMC 90. That fitting is a listed transition fitting. We don't really list fittings for concealment. So are you telling me that has to be exposed? I can't bury that fitting underground?
Okay.
That was obviously never the intent, but unfortunately, that's what it says. So hopefully nobody digs that deeply into this, because really what happened is we kind of screwed up in the 2020 and we made it worse in the 2023. And I'm not making fun or pointing fingers. I know how hard writing code is. I've written a lot of rules. I know how difficult it is to write code and to get it perfect. So, I'm easy to point out a problem, but I'm also not saying that panel 3 is a bunch of idiots. That's not the case at all. It's just, sometimes it's hard to get everybody on the same page and see it the same way.
So is the term fitting defined?
Yes. Yeah, I know for a fact it is. I can't rattle it off the top of my head, but I know it's definitely defined. An accessory like a lock nut, bushing, or other part of a wiring system that's intended primarily to perform a mechanical rather than an electrical function.
Okay, so like a coupling.
Mm-hmm. That's fitting.
So if I had 2 pieces of conduit and I was going to bury it, and I put a coupling in between to hold that together because I needed the length, you're saying that because of F, I would have to make it accessible?
Well, no, because you're not using that fitting at a splice point or a termination point or a pull point, or now under the 2023, a wiring method transition point. You're not transitioning between PVC to rigid.
Yeah, but
because now they're saying, sorry.
It says a fitting identified for the use shall be permitted in lieu of a box or a conduit body where conductors are not spliced or terminated. So if it is spliced or terminated, then it has to be accessible unless it's listed for concealed installation. So when would you have a splice in a raceway or a box that you would not have accessible?
An example would be in 334.40, which talks about the NM cable interconnector device for repairing damaged NM cable or just splicing into old existing NM cable.
Yep.
That's a fitting that we can use and conceal.
Right.
And that one actually is, I believe, is listed for concealment. I think that product specifically is listed for concealment.
Would that be that's not a fitting though?
I think by definition it probably is. Well, yeah, I think it is. I mean, it does perform a mechanical function rather than an electrical function, I guess. Or does it? I guess it's performing both, really.
It's performing both, right? Because it's securing the wire together. It's holding in place. Because I just used one over here. I mean, it's exposed, but I bought it just because I wanted to learn how it was
Mhm.
used. But it does do a mechanical. But then that is probably why F exists, so that you can put that behind a wall and not have it readily accessible, right? So
Right.
I'm trying to figure out what the problem is. When would F give me a problem?
Well, 300.15, the driving language, says you have to have a box whenever you're making a splice or a termination
Right.
or at any pull point
Yep.
or at any raceway transition now.
Right.
Okay, so I am making a transition from PVC to rigid. So the general rule says you have to have a box there. But F says, no, you don't need a box. You can use a fitting.
Right.
But it has to be, but it can't be concealed unless it's listed specifically for concealment.
Okay.
So the transition fitting we would use would be a PVC female adapter and thread, IMC or rigid into it.
Yeah.
That's a transition. That's a fitting. So now F says that has to be exposed. You can't conceal it unless it's listed for concealment. And if you look at the product standard for PVC fittings, I don't think they necessarily list them to be concealed. They just list them. And then the wiring method itself is what allows it to be listed or not listed, or concealed or exposed.
Concealed or exposed. So you would always have to expose it.
Yeah, I mean, a literal reading of it, that's the case.
Yeah, yeah. And if
it's a screw up, I mean,
yeah.
it happens.
Yep.
But fortunately, I think for the most part, fortunately, only pretty hardcore code nerds like me and you are going to catch it.
Yeah.
You know what I mean? I don't see inspectors in the field actually saying, "Hey, you can't bury that fitting that we've been burying for 120 years."
Yeah, I just try to bury the hatchet.
Right, there you go. Exactly. Hey, listen, pal, I'm going camping here in about an hour, and I got to load up the truck and the dogs.
Ah, cool. Where are you going camping at? Where are you going camping?
Just in the Uinta Mountains here in Utah. So we're just going straight up the mountain, a couple thousand feet, and having a nice long weekend. Me and the wife and the two dogs.
Awesome! So, I expect to see a bunch of photos on social media. So make it happen.
I'll do it, man. I'll do it. Okay. All right, guys, take it easy.
Thanks, Ryan. Talking to you. Take care. I'll see you.
Okay. Bye.
All right, that was cool. That was good. And the transition wasn't that bad either. So I know he's going to have a blast on his little holiday. All right, so hopefully, Willie, that helped out. I don't know. All right, there was something else. Okay, so we talked about that. We talked about Monday next week, possibly Tuesday next week, going live from the booth. Monday night looks like, Tuesday afternoon, and Tuesday evening. So at least that's what it looks like at the ASHI convention out of Boston. So tune in Monday and Tuesday. Remember to subscribe. Okay, so I did have a couple other questions. What was it? Question. All right, love the video. Speaking of kitchens being added to the AFCI list, which also requires GFCI. So let me just that and do A10, I think. So, boy. Oh, you can't read that, can you? Love the video. Speaking of kitchens being added to the GFCI list, which also requires GFCI protection, one problem is that many kitchens wired in the 70s and 80s, even some into the 90s, as well have multi-wire branch circuits. All breaker manufacturers I'm aware of have 2-pole GFCI breakers available. A handful have 2-pole AFCI breakers available. But no manufacturer I have seen has a 2-pole dual function breaker. Any chance that would change in the future? So what he's talking about, shared neutral applications. Remember, that's a good question. That is a good question. So shared neutral applications, when you have a device that is a pigtail, so AFCIs, they will have a CT in there. They'll have a core. Some of them provide GFPE. Some of them have GFCI protection. So when you want to provide GFCI protection for, say, a kitchen, a lot of people are just using dual function devices. So dual function. And I'm not aware of an AFCI GFCI device that has that is two pole from any of the manufacturers. I don't think we have one either. So what that means is that what you would have to do is I would say put your AFCI. You can do a couple different things. You can put your GFCI, because we do have two pole single phase GFCI breakers that you can put in the panel board, and then put AFCI receptacles at that end of that first home run circuit. Or if you look at the 2020 code, we give you options to use the I gotta get my glasses back. 210.12 has options for you. You can put the home run circuit in metal raceway. You can put it in a metal raceway. That's pretty much the only thing you can do that would make sense. And then put an AFCI receptacle in the kitchen. Now this is for an existing, right? So what you're talking about is an existing home, and you're retrofitting back into an existing home, which would go above and beyond the NEC requirements, because the NEC doesn't, unless you're pulling a new circuit, all this other good stuff, and you're pulling a permit, right? So it depends on your local jurisdiction and what's required there. But you're better off putting a standard AFCI two-pole breaker in that application and put your GFCI receptacles down below. That's probably how I would do it. That's how I would do it. That's how I would. All right. Oh boy, not me. How does a synchronous motor adjust the power factor by over or under exciting? Wow, synchronous motors. We can use synchronous motors to provide power factor correction. I tell you what, not me. I have never done that. What I have used is power factor correction capacitors. They talk about the synchronous motor and over and under excitation and all that jazz. I have not personally done that. I'd have to do some homework, answer that question. I can't answer that one on the fly. But I will put that in my little bag of goodies. So I got to keep a running tab on these questions, because that is a good question that I do not know the answer to. IAEI Eaton Tech Talk. So I am going to add to Q&A Friday a question from not me. Not me. Insight, how does a synchronous motors used for power factor correction? I'll look that up and I will get you. I've not done it, so I can't speak from experience, and I'm not gonna BS you. So I'm gonna take that off because I don't see anybody coming in over there. All right, so Willie Snyder, Nihad El Sharif. Okay. Oh, what's that? All right, so Russ LeBlanc. Yeah. Okay. Should have a list. Do I have to pull a neutral to my fire pump equipment when connected to the line side? if I have a barrier inside a panel board such that all energized parts, when I take the cover off, are there any exposed parts per 70E? Exposed parts are exposed parts. So if you have a barrier over anything that's energized, then you don't have exposed parts. That's just a discussion around barriers inside of a panel board. So if I have a panel board with a main, I have a line side barrier, and I take the cover off, and I don't, and say I turn the main off, I don't have any exposed parts because I've got barriers in place. That's just reducing the likelihood from a shock perspective. So I'd say your shock risk is low. Arc flash might be a different story because there's energized components inside that, but they're not exposed. So, and I think if you read the NEC or NFPA 70E, and they talk about exposed energized parts, if you have barriers in place and they are not exposed, then they're not exposed, regardless. All right, and I think I got some of these already. All right, so let's take a look real quick at let's take a look at a we are going to take a look at a 112 kVA transformer. If you're following out there on IEI News Live, we said we were going to talk about the 112.5 kVA transformer and a 75 kVA transformer, but we did not get to the 75 kVA transformer at all. So what I am going to do is try to cover the, we didn't get to the 112.5 at all. So I am going to, I'm going to grab and we're going to do the 112.5 transformer. So I just have to find the presentation so I know what side, what the details were for that. PowerPoint 75 kVA, that's part 3. 75 kVA part 2 was selective coordination. And there it is. Yeah, Nihad, it does. And I'd love to be able to show that, how that works. I don't know if you have any of that information. Okay, so here we go. 125 kVA, right? Or 112.5. Got a nameplate. I'm looking for the nameplate. All right, here we go. All right, so that's all I got to do is this. So what we have is a 112.5 kVA transformer, primary 480, secondary 208, 480, 208. We have 4.17% impedance, 4.17% impedance. And I think that's all we need with regard to that. So let's do a calculation of the full load amps. Full load amps is 112.5 kVA divided by the square root of 3 and divide that by 0.208. Make sense? Do the math. Boom. 112.5. 3 square root divide 0.208 divide 312.3. So primary full load amps. Primary is 312.3. And then to do the, I'm sorry, that's secondary. 312.3. To do the primary, we got a point 0.48. So 112.5, 3 square root, divide 0.48, divide 135.3. 135.3. Okay, so remember our primary overcurrent protected device based upon primary overcurrent protected device. Our maximum is 2.5 times 135.3. 135.3, 2.5 times, whoa, 135.3, 2.5 times 338.25, so 338. I can't exceed 338, so I got to go to the next one down. And that's what, a 300 amp? I got to use the 240 dot. Got to go to 240, and you got to go to 240 dot. What's your 240.6? And that is 300 amps. Okay, so whoa, standard size is 300 amps. So that would be a 300 amp device. What we typically use is 1.25, right? So 1.25 times 135.3 is 1.25 times 135.3 is 170. And I don't have to go to standard, so I can use a 170. If I can get whatever size breaker I'll get in, and what we'll do is that's our starting point. When we go to SKM, I'll just we'll see what breakers are available. We'll try to go with a thermal mag. All right, secondary. I have primary and secondary protection. I'm always going to have secondary protection. So my maximum based on the table is 1.25. That's 4. Remember, we're looking back in Article 450 times 312.3. So 1.25, 312, 312.3 times is 390. I can go to the next higher, so I can go 400. So I'm going to make this a 400 amp. And this is a 400 amp panel board. 208 panel. And I'm going to make that one. We'll take a look, and we'll probably try to make that I don't know, maybe a 200 amp. Or maybe even a 150. I don't know. We'll take a look in that ballpark once I get on SKM. All right, so I know my secondary, and then my conductors. I have to have enough ampacity. Just lost my tap rules. I have to have enough ampacity, so I'm going to go to 310. I'm going to need to get a new book. 310.16, 310.16, 75 degree C column. So that's either 200, and that's a 400. So I'm going to do this. Get rid of all that. All right. So this is C1. This is C2. Conductor 1 is going to be. I need so if I do 200 amps, 3/0, 200 amps, 3/0, 175 is a 2/0, and I know all you guys know this off by the heart, but I don't. And 150 is a 1/0, right? Now, conductor 2, I need 400 amps. I'll probably go with 2 3/0. What would you do? Would you go with 2 3/0 or would you pull 1 600? What would you do? Love to know. What would you do? Anyway. Okay, so I am going to grab this. And we're going to do this one together. I'm going to cancel. We have that over there. Let's do that. Do that. Bring up SKM. All right, we're going to bring SKM up, and we are going to get a single run 500. You would do a single run of 500. For a 400 amp breaker, you would put 300 amps worth of conductor on a 400 amp breaker. I think what I would do is make sure that the ampacity of my conductor is protected. Based on 240, I have to protect a conductor at its ampacity. I can't go to the next higher from a conductor size. I can go the next higher from a load calculation, but my conductor ampacity has to be greater than my overcurrent protective device amp rating. All right. That's our 75 KA. So I'm going to do this. I'm going to go project, cancel, cancel. I'm going to go project new, and I don't know what that one is. I'm going to create a new folder, 112.5 kVA Friday. Open 112.5 kVA Friday. All right. I plop in a transformer. Yep, I got a conductor. I'm going to plop in a transformer. I have a primary conductor. I have a secondary conductor. I need a bus. I need a circuit breaker. And to the bus, I'm going to connect a utility, which will be my way of representing an available fault current. All right, so let's start with this transformer. I have a delta Y ground. I got a 480 volt primary. I've got a 208 volt secondary. Bus voltage is 480. Secondary is 208. Transformer impedance. We said transformer impedance was 4.17. So I take 4.17 times 0.9, 3.753, 3.753, give it an 8, X to R. Why did I do a 0.9? Because plus or minus 10%, maximum available fault current will be at a 0.9. Lower the impedance, higher the fault current. All right, so damage curve. Damage curve. So if when I look at the locked rotor inrush, the locked rotor amps. Locked rotor. It's a transformer. The inrush current. Geez, when I look at my inrush current, we looked at some tables and we did some homework with regard to a couple manufacturers, and we saw none of them got up to 12. They got around 8 to 9. So I'm going to make this a 9. So it's 9 times the primary full load amps for 0.1 second duration. It'll be a data point, and I have to make sure that my instantaneous of the primary overcurrent device is greater than that number. All right. I will just do my 3-phase fault, and that'll be that. So there's my transformer. Primary conductor, we're going to try to put a 1-aught conductor. I'll use copper. And since the delta is on the primary, I don't need a neutral, so it's a 3 conductor with a grounding electrode, the equivalent grounding conductor. 3 conductor plus ground. And we said we were going to put a 1-aught in, and we'll make it 25 feet. 1-aught's going to be 150. We're going to see if we can get away with 150 amps. And so that is what we have there. We'll make that an infinite bus. That way, if I do infinite bus, when I do my selective coordination with the fault current values, I will know that my selective coordination pairs will work regardless of what the actual fault current is. So if I'm in the design phase, I want to make sure that that works. But now I run the risk of spending too much money on overcurrent protective devices, but you have to weigh that. All right, so on the secondary, we have a conductor coming off of the transformer, and we said that was going to be a 3-aught. Library, copper, PVC, and we'll make this a 3-aught conductor. 2 of them. No, 1. No, 2. Yeah, quantity 2, and we'll make it 10 feet. All right. So that's the conductor. That will land on a circuit breaker, which will be connected to a bus. And I will have another circuit breaker downstream of that. All right, so let's see how we did. Excitation gives leading. All right, so FN, Control A to run the study. We'll do a short circuit. Now you'll notice it says ANSI versus comprehensive. ANSI is what they used to call A fault in SKM world, and comprehensive was DAPR. The difference there is the ANSI method uses rules of thumb, and it will create an impedance diagram with a real and a reactive component and do your network reduction. So comprehensive will generate a number. It might be a little bit different than ANSI because it does a lot more math in the background. I always just go the ANSI method because I can, I have one fatal error, because I can select and actually do it by hand and verify the numbers. All right, so transformer, nominal KVA. I didn't put the KVA in. Nominal KVA is going to be 112.5. Full load KVA, 112.5. And then we do a Control A and run. All right, so my fault current at the secondary. Run data block format. CD, apply, close. Oh. 7,955 amps. 10K breakers every day of the week, twice on Sunday. All right, so now I know my fault current. Let's plot my curves. Oh, I haven't picked the breaker. So we said on the primary, we were going to start with a 150 amp breaker. Remember, to work correctly, in any of these software applications, you have to filter everything to Eaton or Cutler Hammer or Westinghouse. Otherwise, it just doesn't work. So what I'm looking for is a 150 amp breaker. I can get that's an FD single pole, an FD breaker. Let's do an FD breaker. FD 150. So I'm gonna pick up an FD 150. FD 150. 150. All right, so I got an FD 150. Down a little. So that is an FD 150. My secondary, we said, was going to be a 400 amp breaker. I go to library, and I need a, remember, I'm going to put a thermomagnetic, and let's see if we can get this done with thermomagnetic. You have to filter it to Eaton, Cutler Hammer, Westinghouse, and then I look for a 400 amp. I'm going to look for a 400 amp molded case circuit breaker. It's probably going to be an L frame, LD, because it's simple and free. 400 amp, 400 amp. I'm going to set the instantaneous as low as I can for the secondary. And now let's plot the curves. So I pick that one. I'm going to pick my transformer. And I'm going to pick my primary breaker. And I'm going to say, go to TCC. And we'll do transformer protection. Transformer primary, secondary. All right, there we go. So we got curves. Here is what I do. I do this. I do show label. I turn all of that off. And I go run data block format. I have TCC close. And that gives me the names. All right, so I have my transformer damage is the blue line. Transformer damage, this green circuit breaker is the 150. So I'm going to move that up and the red one down. So that's my primary breaker, and you'll notice that it is clobbering my inrush current. So that's an FD 150. Let's do this. Before I get off of a 150, I am going to try to pick a different circuit breaker. Let's go to an electronic circuit breaker. And go to a 150. I'm going to try a K-frame. Try a K-frame breaker. See, this is the difference between a molded case and, ooh, there we go. Look, I can actually do that. That's 250, but well, let's see, 150 is where? 50 is about right here. There we go. So 150, and add a delay. Bring that down. See, I can do it with an electronic trip unit, but now that is a 250 amp frame instead of a 150 amp frame. That's going to be more expensive. Let's grab go back to a thermomagnetic. I already tried an FD 150 FDB. I'm going to try an HF. Nope. Still an FD. I think that I'm not going to be able to do a 150. Ain't going to happen. So I'm moving it up to a 200 or a 170. Let's do a 175. Library, 175. Can I get a 175? Nope. I'm going to do a 200. Going to a 200 amp breaker. 225. I can do an FD. I can do a J. So we're going to do a JD breaker. We're going to do a JD breaker, and we're going to make it a 200 amp. Here we go. And I can move the instantaneous. So there it is. It works. See how I'm staying away from the inrush current? I can adjust my instantaneous. I'll have to document that so that the installer can set the dials. All right. So I picked that breaker, and I'm going to pick, that's the primary breaker. Secondary breaker works fine. Those are both thermomagnetic circuit breakers. I got a 400 amp on the secondary, 200 amp on the primary, and they're both thermomag. I'm providing adequate protection for the transformer. And let's run an arc flash study. So I go to run. Oh no, what did I do? I changed the primary to a 200 amps, but I left 100 amps worth of conductor, 150 amps worth of conductor, so I got to make this a 3-aught. And then I need to rerun the short circuit study. Run, close, run, balanced system study, run, close, run, arc flash, evaluation. All right, so I'm going to use the 2018. My fault current, see if there's anything I have to change on here. I don't. I am going to do all standard for the clearing times. I'm going to do bus plus the line side. I've got to consider line side propagation. I'm going to hit OK. Incident energy at that panel 4 is 16 calories. 16 calories. Now, let's run a scenario. We're going to go project, scenario manager. I'm going to clone it. And then I'm going to activate the clone. So now what I'm going to do is I am going to, back to the one line. I'm going to make a small change on the secondary. I'm going to disconnect this. I'm going to disconnect the primary and secondary so that breaker is by itself. I'm going to clone this conductor. Put that on the secondary. I'm going to connect that breaker to that conductor, and I'm going to put a bus in between. I think I can do that. Oh, what am I doing? Yeah, that's good. I'll do a Control A, run. All right, so I have a main lug only panel downstream. I made a breaker, basically, I put a breaker in the box up above on the secondary of the transformer. The energy in bus 5 will probably be high, and if the arcing currents are in the instantaneous region of that circuit breaker, the incident energy at bus 4, which will have all of my branch and feeder breakers where I will be likely to do justified energized work, is going to be hopefully low. Let's run a arc flash. Hit OK. So bus 4 is 0.21 calories. And bus 5 is 16 calories. So by simply moving the main overcurrent protected device outside of that panel board, my incident energy in the panel board went down considerably. Now, Eaton sells a breaker integrated transformer, so I can buy a transformer with the secondary breaker built in to the transformer and get these results by lowering my incident energy. Now, the incident energy, obviously, in that transformer or in this breaker in a box or a fusible disconnect is going to be higher, but the likelihood of having to get in that panel board is low. So that's what we did. So we did a 112.5 kVA transformer. We picked the primary and secondary overcurrent devices, and I'll code references. Okay, let's do the code references. My code references for transformer protection are in 450. 450.3b, I believe, is the table. 450. No, yeah, 450.3b is your table. Primary and secondary protection. You can go as high as 250% on the primary. We went at 200%, or we went to 200 amps, which what's 250, 2.5 times 135, 135.3 is, okay, that was 300 amps. So we could have gone up to 300 amps. We went to 200 amps. And we went to 200 amp. We could have gone as high as 300 amps. We tried to get 150 amps, but we were bumping into the inrush currents. So we followed that rule. On the secondary, 1.25 is the maximum size for the secondary overcurrent protection. And the reason we went to the secondary overcurrent protection, because of 408, tells us if I have a panel board on the secondary, 408 dot 408 panel boards supplied through a transformer. 408.36b. Where a panel board is supplied through a transformer, the overcurrent protection required by 408.36 shall be located on the secondary side of the transformer. The only exception is 240.21c1. I can't use 240.21c1 because that requires me to have a single phase transformer or a delta-delta. I've got a delta-Y ground. What is the typical inrush multiplier set at? Is there a requirement in 1584 for a minimum value? No. Wiley Braun, there is no typical for inrush currents on transformers. They tell you the range. I remember 1584 is talking about incident energy calculations. And that the only impact that the inrush current will have on incident energy is where I set my primary overcurrent protected device. That's it. I could put a arc reduction maintenance switch on my primary overcurrent protected device so that I can turn it on and it will reduce the energy in that, but I'll need an electronic trip unit on the primary. In fact, I'm going to try. Well, anyway, I'm doing code references. All right, so 450.3b, 408.36b, 240.21 Charlie tells me my transformer secondary conductors. 240.21. I always keep my feathers numbered for just such an emergency. Yep, 240.21c is your transformer secondary conductors. And we were following C2, but if I did a breaker integrated transformer, I could put as much length between the transformer and the panel board as I want. So those are my code references. I think that's it for the code references. Let me put my thing back. So now, hey, thanks, Doug. Wiley Braun, the 1584. So let's do that. And I do have a little bit of time here. So 240. I'm gonna put this there. Put that back. Now let's do this. Let's go back to our primary overcurrent protected device. Right? Was this guy? We're gonna do this. We're gonna do a project scenario manager. And we're going to clone this. And we're going to activate it. Now we're going to take this primary device and we're going to go back to the library. And we're going to put an electronic trip unit in it. All right? So we're going to put an electronic trip unit. What is that primary? We said it was 200 amps, right? So let's try a... Here we go. See that ALSI? A is for arc reduction. And I'm going to see if we can't model that. So there is my... So this is a KD breaker. So let's do this. Gummit. I got to figure out my settings for a KD with a 310 plus trip unit. So here's what we'll do. We will do eaton.com/TCC. For time current characteristic curves. Go to mold decay circuit breakers. And we will go to a KD breaker. Series C. Boom. So I need a 310 plus, right? 310. Okay. I have 250 amp frame. 250 amp frame. Here's a 250. These are my settings. So I need well, I can even do 175 if I put it on E or F. So here is E. So I could change the size of my conductor. I could put a smaller conductor and still not worry about my instantaneous, my inrush. So what was that? E was 175. Look, let's see if I can do 100 amps. Hey, look at that. I could put 100 amps worth of conductor on the primary. What do you think of that? Huh? What's the full load amps? 135. I can't do that. I don't want to do that. Primary amps is 135. So let's 135. Let's put 150. Let's make this a C. All right. But it shows you have a lot of flexibility. We'll do it. We'll do it based on what we said. We had a 200, so we'll put it on F and keep everything copacetic. But look what I can do to the short time delay. I can put it just above my inrush, lower than the inrush, and you know what else I'm going to do is I'm going to do this. Go to the one line. Here's what we're going to do. We're going to get rid of, we're going to blow this away. Destroy it. We're going to destroy this. We're going to connect this breaker. Whoop. Yep, we're going to connect that breaker. So we just basically got rid of that secondary disconnect. And we put the money in an electronic trip unit upstream. Now, let's run our fault study. Control A, run. Close. Let's go back to run our arc flash evaluation. 2.44. So my incident energy now is 2.44. Why is it 2.4? It's because my incident, because now I'm going off of this. There you go, for on-demand availability, baby. So this is so this short time delay on the primary gets me to 2.44, but But remember, when I separated out that breaker on the secondary into its own enclosure, I had less than 1 calorie, less than 1, which is much better. 2.44 is still a hefty, you can dress for it, but it is still a lot of energy. I wouldn't want to experience a 2.44. But in any case, so now I think, therefore I am. Ooh, what did I just do? Yeah. Okay, look, this is maintenance mode. So I just turned maintenance mode on. So I want to take maintenance mode off. I'm going to put back to instantaneous. Okay, so here's what maintenance mode does. When you turn the maintenance mode on the trip unit, right? So you go to that primary breaker. Let's say you're going to work on the transformer, or you're working on the secondary of the transformer at that panel board. You go to the primary and you turn maintenance mode on. And now it took the short time delay and it made it instantaneous. The transformer is energized. I don't have to worry about that energizing current because it's already energized. I'm doing justified energized work downstream. And look at my incident energy, 0.24. So I didn't break out the secondary. I turned maintenance mode on the primary of the transformer on that feeder breaker. And now I have 0.24 calories on the secondary, just because I turned maintenance mode. But now, Wiley, you have to buy an electronic trip unit for the primary to get a trip curve that has that type of flexibility. When I turn maintenance mode back off again and I go back to instantaneous, now my delay is back in the picture. That is exactly what maintenance mode does for you. You're going to do a justified energized work. You turn maintenance mode on. It changes the trip curve. It goes as fast as it can. If a fault occurs downstream, if you make a mistake, you lock and tag that out. You treat it just like you were going to, if you were going to establish an electrically safe work condition, you're going to follow the rules, which means you have to lock and tag out your overcurrent devices. You're going to do the same thing here. You're going to lock and tag that out in maintenance mode, go down, do your justified energized work, and then you come back and you put the instantaneous back in the picture. That is what the arc reduction maintenance switch will do for you. That's what the electronic trip unit does, and it provides better short circuit protection and overload protection for that transformer. Your electronic trip units can help you significantly. And if you have to move that up, you can. And you're at 2.44 calories without the maintenance mode. You put it in maintenance mode and you are less than a calorie. All right. Okay, so we did a 112.5 kVA transformer. It's not that hard. Relatively simple to do. You can run scenarios when you have good software applications. If you did not have software, you'd have to do some math and do things on paper, but you can do that. It just takes more time. And that is, I think, all that I am going to do today. Not for work, but for our session today, because I just want to make sure that I don't have a meeting. I do have a meeting in 7 minutes. So hopefully you got something out of this Q&A Friday. Thanks, Wiley. Thanks for tuning in. Thank you, David Engelhardt, for tuning in as well. Doug Hostetler, some deep water, but trying to keep learning. Thanks, Doug. Collins, not me, over excitation gives leading VARs. Yeah, it does give leading VARs, but I think what would help, not me and others, is if we can show why. That's what I'm looking for. I mean, I can describe it. I can draw you the power triangle and show you the VARs and how power factor correction works. But it's still not answering the question of excitation. What does that look like? So I'm gonna try to put something together on that. Hey Nihad, Tom, sorry I have another meeting to attend. We'll continue watching this later. Great. Thanks for joining us, Nihad. And thanks everybody out there. Remember to subscribe, hit the thumbs up. We are screaming hot on our membership. I really appreciate it. The followers on YouTube are doing great. Hey, get over there and do some stuff. And subscribe, hit that bell, consider more engagement on the YouTube side. Thank you, everybody. I'm going to sign off. Thanks for what you do for the electrical industry. Thanks for what you do for electrical safety. I hope you have a great weekend. I know Ryan Jackson is out there. Him, his wife, and his dogs are going to have fun camping. I'm going to be in Boston next week. Check me out on Monday and Tuesday. Don't forget, we're going to go live from the booth Monday and Tuesday. And I'm going to create I'm going to call it booth duty. Like Q&A Friday, I'm going to call it booth duty. And I got to create a lower thirds for booth duty. All right. Take care, everybody. Stay safe. See you. Have a great weekend. See you next week. Woohoo! Another Q&A Friday done.